In 2023, a research paper passed peer review at a respected scientific journal. The methodology was sound. The citations were real. The conclusions were original. There was just one problem. A large language model wrote the entire thing, start to finish, in under 4 hours. The human listed as lead author had done almost nothing except submit it. And when an independent team later ran the paper through every AI detection tool available, not a single one flagged it. The reviewers, all credentialed experts in the field, had no idea. That is not a hypothetical. That already happened, and it happened more than once. To understand why this keeps you up at night, you have to understand what peer review actually is. It is the spine of modern science. Every drug your doctor prescribes, every climate model governments use to set policy, every safety standard built into the bridges and aircraft you depend on, all of it traces back to research that was validated by peer review. The system is a filter. It is supposed to catch bad science before it enters the permanent record and starts influencing decisions. In 2024 alone, scientific journals published approximately 5 million papers across all disciplines. Peer reviewers, who are typically unpaid volunteers giving a few hours per paper, are the only human checkpoint standing between a claim and the scientific canon. Now imagine what happens when the thing submitting papers is not a human trying to cut corners, but a system that can generate 10,000 plausible, citation-rich, methodologically coherent papers per day at essentially zero cost. The filter does not just get strained, it breaks. To understand how we arrived here, you need to know what peer review was designed for. When the Royal Society formalized the practice in 1665, the concern was simple. Too many people were publishing nonsense and calling it science. A panel of experts reading each submission was meant to be the solution. The system worked reasonably well for 3 centuries because the bottleneck was always the human on the submission side. Writing a convincing research paper requires deep domain knowledge, months of work, and the ability to synthesize a literature that might span thousands of prior studies. That bottleneck enforced a natural scarcity. Even a determined fraudster could only produce so many fake papers in a lifetime. Yoshitaka Fuji, a Japanese anesthesiologist now considered one of the most prolific scientific fraudsters in history, fabricated data across 183 papers over a career spanning more than 2 decades. 183 papers, from one human, over 20 years, nearly brought down an entire subfield of anesthesia research. That number once seemed staggering. Now think of it as an afternoon's work for a well-prompted language model. The specific incident that cracked this open publicly happened at a peer-reviewed journal in the field of computational biology. A paper submitted in late 2023 used GPT-4 to generate not just the prose but the hypothesis, the experimental framing, and the literature review. The human co-authors, graduate students at a European research university, provided the dataset and made minor edits. The paper sailed through 2 rounds of expert review and was accepted. It was only discovered when one of the students mentioned it, casually, in an online forum. Retraction Watch, the database that tracks scientific retractions, logged the incident and began looking for similar cases. What they found was alarming. In a systematic sweep of papers published in 2023 and early 2024, researchers at University College London identified specific linguistic fingerprints of AI generation in over 14,000 published papers across 17 journals. 14,000. Not suspected, not flagged for review. Published, indexed, and already being cited by other researchers building new work on top of them. The contamination had already entered the bloodstream of the scientific record. Here is the part that overturns the assumption most people carry into this conversation. The assumption is that AI-generated science is obviously wrong, obviously hollow, and that experts would catch it. The reality is nearly the opposite. When researchers at MIT ran a controlled experiment in 2024, presenting panels of domain experts with a mixture of AI-generated abstracts and human-written ones, the experts correctly identified the AI-written text only 48% of the time. That is statistically indistinguishable from random guessing. Flipping a coin would have performed equally well. The reason is not that the experts were bad at their jobs. It is that modern language models have ingested effectively all of published science. They do not hallucinate random sentences. They generate text that is statistically consistent with the patterns of real scientific writing because they were trained on real scientific writing. The style is right. The vocabulary is right. The argument structure is right. What is missing is something that a 2-hour peer review was never designed to catch, whether the experiment actually happened. Reviewers assess plausibility, not ground truth. And AI is extraordinarily good at generating plausible text. The mechanism that makes this work is worth understanding precisely, because it is not what most people imagine. A language model like GPT-4 or Claude does not understand science the way a researcher does. It does not have a mental model of the physical world. What it has is an extraordinarily detailed statistical map of how scientific concepts relate to each other in text. When you ask it to write a paper on, say, the effect of a specific protein on tumor suppression in pancreatic cells, it does not reason about biology. It asks, in effect, what text patterns are most likely to follow from this prompt, given the millions of biology papers it has seen. Think of it like a musician who has memorized every song ever recorded and can compose a new piece that sounds exactly like a real song, in any genre, on demand, without ever understanding what music means emotionally. The output is structurally indistinguishable from the real thing. The counterintuitive part is that this makes it more dangerous, not less. A system that understood science might know when it was wrong. A system that only mirrors the patterns of science has no such breaks. The complications here are real, and they compound each other. The first problem is what researchers call citation pollution. When AI-generated papers get published and indexed, they become source material for future AI systems training on new data. The scientific literature starts to eat itself, with models training on model output, errors reinforcing errors in a loop that is very difficult to detect or unwind. The second problem is asymmetric effort. It takes roughly 40 hours of expert time to write a rigorous rebuttal to a published paper. It takes about 4 minutes to generate the paper being rebutted. Fraud at scale can now permanently outpace correction at scale. Several major journals, including journals published by Elsevier and Springer Nature, announced updated AI disclosure policies in 2024, but compliance is voluntary and enforcement is effectively impossible. The people submitting fraudulent papers are not going to disclose that. And the tools built to detect AI writing, like GPT-0 and Turnitin's AI detector, have false positive rates high enough that using them to automatically reject papers would eliminate a significant volume of legitimate human work. For you personally, this is not an abstract problem about journals you will never read. If you work in medicine, law, engineering, finance, or any field where decisions are grounded in published research, you are already downstream of this. Drug efficacy studies, financial risk models, engineering safety thresholds, dietary guidelines. These are all built on literature reviews that are now, quietly, compromised. By 2027, multiple major research universities have begun requiring authors to submit raw data and lab notebooks alongside manuscripts, precisely because text alone can no longer be trusted. If you are a researcher, a clinician, or a policy analyst, that shift is coming for your workflow faster than your institution's IT department is prepared for. The actionable move right now is to look past the abstract and into the data. Does the paper link to reproducible raw files? Is the methodology specific enough that someone could replicate it independently? Those questions